Okay, sir, we'll start.
Sure.
Okay, thank you. Good afternoon, everyone. It's 3 o'clock, so we will start on time as has been the practice. Once again, I'm really happy to host you all for this Spectratix knowledge series, and it's a special session wherein we have Dr. Sambhav Kumbhani, who is the Chief Business Officer at Center for Sophisticated Instruments and Facilities at IIT Bombay. Uh, a brief introduction regarding what this Spectratix knowledge series, sir. Yeah, Spectratix knowledge series is actually a series of discussions. You can say it's not a lectures. This is more of a series where we try to have discussion regarding what is happening with respect to the latest things that are happening related to pharma and the associated fields, so that it becomes means as we go ahead with our careers or as we leave our colleges, we tend to forget our theory part, so and we stop learning, you can say. So this is an attempt so that at least once in a week we go back to our basics and also get to restart or that process of learning. So that's the main aim with which we have started this Spectratix knowledge series. A brief introduction regarding Sambhav, Dr. Sambhav, sorry. Doctor has joined IIT Bombay as the Chief Officer for CASF. He in his current role he wants to serve as a bridge between industry and IIT Bombay. From whatever interactions I had with Sir, it's the means he is of a different league and he wants to take industry with him. He brings with him 16 years of experience in the professional experience, with 8 years exactly between academia and industry with Sir. So, and he has already worked with many reputed analytical instrument manufacturing companies like Mettler Toledo, Bushi, and Malvern Panalytical. He has held diverse roles with respect to like application scientist, marketing specialist, sales manager, and a business development. So I guess everything has been taken care from, every section has been taken care, right from theory or the technical aspects to the non-technical aspect. Okay, so his strong technical expertise rooted in his PhD and postdoc work brings expertise in instrumentation and analytical chemistry. And today's topic will be concentrated on the importance of X-rays in pharmaceutical industry. It's over to you, sir, and thank you for accepting our invitation.
Right. Absolutely. My pleasure, sir. Thank you for the kind introduction. And I hope to do justice to your series and the goals of this series. So I hope everyone is still able to see my screen comfortably.
Yes, sir. Fine, sir.
Yes. Okay. So let me start with a question only, since you said it's more of a discussion. So let me ask everyone a question here, like where do you think X-rays are most used today, and for what purpose, right? So maybe you all can quickly type in your answers in the chat, like where you know that X-rays are being used today.
You can directly answer also. Means
Or
all are
answer, of
unmuted.
course. Yeah, yeah. Okay, shy people. That's why I said chat. If you don't want to say, come on. You know somewhere. You know X-ray being used for sure. Okay. In the interest of time, I'll move on. But essentially, there's two places where you know them the most: your medical X-rays, the X-ray machines that hospitals have, and all your airport and mall and everywhere security scans. So these are the two places where most of the time X-rays are used. But the fact of life is, X-rays are being used everywhere in every industry you can think of: food, healthcare. There are a host of applications. I can give a dedicated talk for each of these arrows for a couple of hours each. So, food and healthcare uses X-ray technology. Construction and building material uses. The cement quality is being checked by X-ray day in and day out. Automotive, your battery performance, your car part performance, your car assembly, all that also goes through a lot of X-ray inspections. Metal mineral mines. So whenever you mine something, you want to know how well or where to mine rather in the first place. Like within the same mine for aluminum, for example, uh, there are different parts of the mine where there will be higher aluminum content versus somewhere else, right? So X-ray can help you identify that. Energy renewable, solar cells, solar panel quality can be checked using X-rays. Yeah, there are many applications in energy. Polymer quality, polymer type, all that can be identified using X-rays. Fabrication and mechanical tools, again, they are very much dependent on X-ray. Semiconductor cannot survive without X-ray. It won't even begin without X-ray. And chemical, pharmaceutical, again, any type of chemical pharmaceutical industry needs X-ray a lot. And today, as you all know, we are going to focus only on pharma. So let me reintroduce my topic to you now in pharmaceutical industry. But what I'm really going to talk about advanced characterization techniques of X-rays in drug and safety and quality. All right. So how analytical techniques help in pharma is principally what I'm going to talk about. So let's start at the very beginning. What is an X-ray? This. I'm sure all of you remember your electromagnetic spectrum. X-rays are right here. Right? So this is the place. They are very high energy and low wavelength. Right. Dr. Wilhelm is the one who invented X-ray first in 1895, I believe, and this is truly his wife's hand with a ring on it. This is the first ever X-ray ever taken, by the way. Pretty cool. So, what kind of X-ray techniques exist today? Right, there are many more. Uh, Principally, they are divided in the way the X-ray or the light is interacting with matter. When you hit light on a matter, multiple things happen. Light can be absorbed, light can be transmitted, light can be diffracted, refracted, or scattered. Right, different things can happen. And in principle, that's exactly what the techniques are divided also. So if when the light interacts with matter and it diffracts, we call it X-ray diffraction or XRD. There are many types of XRD. The two main ones that we know are widely famous are X-ray powder diffraction and single crystal X-ray diffraction. These are the two main types of XRDs. Then, when X-ray hits matter, it can scatter light. Then we call it X-ray scattering. Now, there can be small angle X-ray scattering or wide angle X-ray scattering. So, powder XRD and wide angle XRD used to be two different instruments, but the technology has evolved so much that essentially a powder XRD can do wide angle X-ray scattering now. So, in principle, honestly, the scattering part of it now only has been limited to SACs because this pretty much covers the sky. But in theory, these are the two main ways of scattering. If the light is absorbed, X-rays are so powerful that they're not going to stay there. They're going to affect the sample. And the ultimate outcome of absorbing that light is basically release of fluorescence out of your sample. We are going to talk a lot more about this in my future slides, but in principle, when I say absorb, I'm really talking about fluorescence here. But absorption is the first step of the process. So there can be two major categories of XRF, energy dispersive or wavelength dispersive. And then there are many subcategories and all which we will talk about in future slides. But essentially, EDXRF and WDXRF are the two techniques. And then the light can be transmitted. And when the light is transmitted, we use it to image things. So the radiography or the scanners that I just showed in the previous picture, they're both called radiography. Essentially, when you take a photograph by placing a sample in front of the detector and X-rays are hit, that's called radiography. A single 2D X-ray image is a radiography. Okay. Then there is something called as tomography and microscopy, X-ray CT and X-ray microscopy. So yeah, these are different techniques. Again, I'll talk a little bit about them in my future slides. But covering all those instruments and their application in pharma is going to take me an entire lecture, full lecture series, like 6 months lecture series. I don't have that kind of time. So what I'm going to do is focus on this three main instruments, which are the most common X-ray analytical techniques used today in pharma, right? So powder XRD, EDXRF, and micro CT. These are the three ones I will talk about today a little bit in terms of theory, what the instrument is made of, what's the working principle, and what are some of its application in pharma. Okay, so let's start with. Uh, oops. No, before I go, sorry, before I move on, I do want to talk about one thing. Since I talked about light interacting with matter, let's talk about matter also. This is again very basics, but I want to remind you all of it. So matter can be of three states, right? Solid, liquid, gas. For the moment going forward, we are only going to focus mainly on solid state, right? And solid state can be either amorphous or crystalline. Crystalline is an extremely ordered way of arranging material in solid. Amorphous is absolutely random way of arranging material, right? So these are the two main types of solid states that the world has created, or the nature has created rather. Now let's enter X-ray powder diffraction. Basically, this one line summarizes its entire principle. It's a gold standard for solid state characterization. If you have a solid material that you want to characterize, X-ray diffraction is the right way to do it. So what is a crystalline material? Again, a little bit of revision. A crystal usually has six main parameters. The three sides, A, B, C, right? This A, B, and C. These are your three sides of a crystal. And then each of the two sides will make some angle with your crystals. That will be your alpha, beta, gamma angles. And the permutation combinations of this A, B, C, alpha, beta, gamma can generate seven types of crystals. You know this, the cubic crystal, hexagonal crystal. You must have studied all this in your 11th, 12th, but just a reminder. This is how they are, and any material on Earth can be uh, identified with one of these crystal types. So far, we don't know any other way of making a crystal that nature can do, right? So knowing this parameter, if I can find out the A, B, C, alpha, beta, gamma parameter somehow, I can know what the crystal looks like. Yes. And imagine if I can see a plane, right? This entire section is called one plane. And if I know where the one plane is with respect to the other plane, then I can also know what the structure is, right? So that's essentially what XRD does. XRD is a tool used by scientists to basically find the atomic and molecular structures or the crystal structures of stuff. Okay. In principle, we are looking at identifying different lattice planes of the crystal. And once we know the planes, we can predict the structure. Okay. This is how the original way, like the very initial days of XRT used to be. Basically, you would take an X-ray, you take a crystal, and you hit it with X-ray, and you collect it on a photographic plate. What the X-ray beam is producing, and basically each dot here is a representation of the actual position of the crystal structure inside this crystal. Now, this is more of a 3D image actually. If I take a vertical slice, just one single thin slice of this radiograph, then all I will have is different dots, right? One dot, like dot on one line. And then if I take that dot and pull it up like a mountain peak, what I produce is an XRD spectrum today. Okay. I will come to it in a minute, but this is essentially what it is. Anyway, so here's the most simplest example of why XRD is so important. We all know both graphite and diamond are completely carbon, 100% carbon structure, but one is the toughest material we know, the other you can break it with your hand. So what makes diamond so strong and graphite so weak? It's the structure, the way the carbon atoms are arranged in its lattice defines how the material behaves. So this is an extremely important property that we use in our day-to-day life. So in terms of principle, it basically works on the principle of Bragg's law, and lambda is to the sine theta. Again, your 12th standard physics. But in principle, as I said, there is order in a crystal, and then there will be different planes across that crystal. If you look at this particular plane, and when we hit X-rays to that plane, it interacts with the atoms and it diffracts the light. And the angle at which it refracts is going to define the distance between the two planes. So if I keep my wavelength, the X-ray wavelength constant, I give a very specific known exact wavelength of X-ray incoming on the material or my sample, then the angle at which it refracts would directly be proportional to the distance between the two planes within the atom. And knowing these planes will let us know what the structure could be. But it's not as simple. There are a few key physics steps or the principle that must be followed. One, the Bragg law must be followed, and it must produce a coherent or a constructive interference. In the sense, when I go back, when a sine wave comes in, and for some reason it hits at a wrong angle, what will be produced is a destructive interference, and then that will not produce your diffraction pattern. Okay? So it must be a constructive interference. One, Bragg law must be followed. And second, the angle should be coplanar to the normal of that plane. So if this is my normal for this plane, this particular base of the cube, this plane, normal is obviously 100% up, right? So for this normal, this I and D, or the incident beam and the diffracted beam, has to be in the same plane as the normal. So this square is the plane for the normal, and they are in the same plane. Then yes, a diffraction pattern can be collected. This is real life how it looks like. You have an X-ray source, you have your sample, and you have your detector, and within your sample there will be many different planes, as you can see. So this horizontal lines here is one plane which is perfectly normal to this X-ray angle right now. So this X-ray source and detector are completely coplanar to this specific normal right now. But it is not normal to this or this or this or this. So none of those will be measured, only this will be measured. But then I do want to know about all this, right? I cannot miss information what is available here. So to include all those information, we must change this angle that is being formed by the source and detector, what we call as 2 theta, right? Because of the 2 theta angles. So this is essentially what we call an X-ray instrumentation. And this ring is called as a focusing ring. And in an X-ray instrument, the X-ray tube and the detector move on this ring and create different angles. And each angle would allow you to reach one of the normals and become coplanar and then measure that part of the sample. Okay. So here's a live example. And okay, wait, there's one more difference. In this particular crystal, the D spacing is very different from the one right below it. You can see this is a very close D spacing versus very far D spacing. How do we account for that? This is how we account for that. This is still the same logic. All three of them in right now, for example, are completely in a horizontal plane, and their normal is vertically up always. My tube is at the very bottom right now. My detector is also at the very bottom. We move it to its, and then we turn it on. We turn on our X-ray, we measure our diffraction, but there will be no peak because the angles are wrong. So we move to the right angle. As soon as we move to the right angle, the first peak shows up for this particular type of crystal. Then we move further up, and then this is the right angle for the middle crystal. Then we move more up, and then we have the right angle for the third crystal. And this is how you generate your X-ray spectrum in real life. So in real life, things are not that perfect. You don't only have one material, right? We have multiple things combined in a sample. So this is a very simple example of silica. These are all different types of silica. See, SiO2. Quartz is SiO2, glass is SiO2, and this is another mineral form of SiO2, right? If I mix all these three too, so these are pure. The individual spectra or the individual diffractograms that you are seeing are very pure material diffractograms. But when I have a true mixture of them, this is the kind of diffractogram I get. Okay. So you can imagine, right? In your mind now, you can clearly see that this big hump must be the glass, and this specific big peak over here is this peak. This big peak over here is this peak, and from that information, you can kind of, if you want to backtrack, you can always say, oh, this has one, two, three, this three materials in it, and essentially that is what we do in an XRD real life also. But in a typical XRD spectrum, the information that we get is all here. First, that we looking at the whole pattern, like I said, looking at the entire pattern, we get what kind of phases might be present in it, and in how much concentration also we can find. So this is the first information we get in a typical XRD. Looking at the position, where the peak positions are, like where the peak, at what 2 theta angle the peaks are coming up, tells you about the lattice of your lattice planes about of your crystals. How thick the peaks are, or the area under the peak, tells you the crystallite size, how big the crystals are, how small the crystals are. Basically, bigger the crystal, sharper the peak. Okay. And finally, we can get how much is crystalline and how much is amorphous. So here's a cool, if you don't take away anything from today, but you can take this away, the simple lesson. In an XRD spectrum, if you have a flat background, like horizontal background, you basically have no amorphicity in your sample. And if you have a hump in your diffractogram, then you have amorphous material in your sample. Ordered, disordered. Okay, glass is an amorphous form of quartz, or rather, quartz is the crystalline form of glass. Okay, so calculating the area under, or calculating the hump size will give you the percent amorphicity, or percent whatever else is left is percent crystalline, right? Something like that. So you can find the percent crystallinity, percent amorphicity also from an XRT. Any questions at this point before application in terms of theory of XRD? Okay. Once. All right, let's move on then. I guess I'm doing a very good job, or you guys are not enjoying one or the other. Anyway, so first and most common place where XRD or X-ray powder diffraction is used is identifying a polymorph. So essentially, I'll give a lot of details about polymorph in coming slides, but polymorph helps you distinguish between materials of similar nature. Okay. It also helps you, as you can imagine, to find the crystal structure within your powders. So, you could have excipients or API that are crystalline in nature, and you want to make sure that it is pure in pure form. This is where it will help. You can obviously find how much is crystalline, how much is amorphous. That is very critical, because the final tablet formulation would depend on percent crystallinity and amorphicity. Because your formulation is usually in a powder form, and your final drug is in a tablet or a capsule form, right? So if it's a tablet, it has to undergo some form of pressure and all that. And how much amorphicity is in your material will define how much pressure it can handle to become a tablet. So all these parameters are very, very critical. Solid form stability, it is used, but there are other better techniques to do that. Hybrid and hybrid transitions are very critical. There are many chemistry will remind you, right? CaCO3 to H2O. There are water associated with a lot of these excipients, and we need to know what happens if it loses its water at higher temperatures and things like that. Again, process development and in-process control, XRD is used, but there are better techniques to do this. Batch release, yes, it is very critical. You do not release a formulation batch without confirming with XRD, for sure. And of course, you want to confirm the equivalence, like that this is the same pharma drug as from one company to the other. Aspirin from Cipla, aspirin from GVK should be aspirin. That can be confirmed using XRD. So what's a polymorph? Again, this is the most simplest example: diamond versus graphite. So now you can obviously imagine why graphite is so strong versus why graphite is not so. But if you took an actual XRD of it, this is how it looks like. They are very different spectrums. Jamin Asman, literally, right? So it's very easy to identify between polymorphs. So here's a real world example of a pharma. This is an alprazolam tablet form, right? There is one, it has two polymorphs, right? Morph 1, morph 2, for example. And this is the actual batch that was produced. So this is one of the batch production, and they are confirming which polymorph is dominant in this. Okay, you can very clearly see that if it was polymorph 1, this should have been a much bigger peak than what you have it here. Versus you can clearly see this is a matching peak to form 2. Similarly, you can pretty much go through the entire spectra and compare it like that. And this is essentially what we do. That's what we called as comparison to reference. These are pure material reference database, right? And we compare it to our actual sample, and we can quantify also exact concentration of polymorph 1 and 2 in this actual batch. And that quantification process is known as retooled refinement. Okay. So yeah, it's not that the morph is 1 is completely absent. So if this was completely flat here, this 1, 2, 3, 4 peaks were not present here, and it was just a plain straight background, then it would have been clean batch 2 only. So like a morph 2, not batch 2, morph 2. But it's not the case. There is some concentration of it available, but it is very obvious that it is not 50-50. Just looking at the spectra, your common sense will tell you that this is not a 50-50 combo. This is more like a 70-30 combo, because the intensity is roughly a third of what it should have been if it was a 50-50 combo. I hope this makes sense. So just like your mass spectrometer or FTIR or any other similar analytical techniques, we have a database. The world has created an entire database of all kinds of material measured using XRD, pure materials measured using XRD. Some of them are this ICDD. They have different versions of it, but ICDD is the one company that maintains this database that you can use to compare your actual sample to. Cambridge Structural Database is one. Crystallographic Open Database is another one. JCPD is another one. Japanese Structure something. So there is many different databases available. So based on what kind of research you are doing and which one of these industries that I showed in the beginning you are representing, you can choose one or the other set of database to buy when you buy your instrument. And based on your database, you can do your work of comparison, things like this. However, obviously, because we are in pharma, there is a USP guideline available. US Pharmacopoeia defines everything pretty much these days. So I'll read it as it is for you, because it's Pharmacopoeia, right? We need to follow it. So demonstration of a non-equivalent structure by a single crystal XRD is currently regarded as the most definitive way of identifying the polymorph. However, powder diffraction is a nice way to support it. So with this one line, I principally explained you the entire single crystal XRD usage also. If you remember back in my original slide explaining all the instruments, the diffraction had two main types of instrument, either powder diffraction or single crystal XRD. So single crystal XRD is basically used for this. It is the most accurate way of getting the exact crystal structure. What powder XRD cannot do is definitely tell you difference between two chiral structures, for example. Single crystal XRD can do that. How it works, maybe in some other presentation I'll explain, but single crystal XRD's job is to ensure that it gives the exact structure of every sample it measures. But the limitation is it has to be pure single crystal, whereas the advantage of powder XRD is it can have a mixture of things. So a single crystal XRD cannot measure this batch. It can either measure form 1 or form 2 only. This is where single crystal is used. I hope this makes sense. Anyway, there are other techniques, of course. There are many other great techniques like thermal analysis, TGA, DSC, TGDTA, hot stage microscopy, spectroscopy, IR, FTIR, NMR. All of them together actually give you the final structure. No one technique can reliably, confidently tell you what the structure is. It's not possible. Okay. Here's another cool information that XRD can do. You, the modern XRDs allow you to make the measurement in non-ambient condition. Higher temperature, lower temperature, higher pressure, lower vacuum, high moisture content, low moisture content, things like that. You can do all that. All right, and then up to very very high temperatures, all the way up to 2200 degrees on the positive side, and all the way up to liquid helium temperatures, 11 Kelvin on the negative side. Same thing with pressure. You can go really high pressures or you can go really low vacuums. All that is possible. Anyway, so this is a great example of what happens to a substance if it is heated, and you constantly measure the XRD while you are heating. So as you heat the sample, in principle, the spacing between the two lattice plane is increasing. And as the D value goes up, theta goes down. And this is your theta. So the black line over here, the outside one, is actually at room temperature. And then you are heating it. So your spectra is shifting towards left. And if your spectra shifts towards left, that means the D spacing is going up. That means your structure is becoming weaker and weaker. Yes. And also another cool thing that we can see here is at higher temperature, something new formed in your sample, which showed up. Some new chemistry happened, which is also observed. So that's essentially what we can study using XRD at higher temperature. Similar things can be seen under vacuum at higher and lower moisture content and things like that. So the moisture part of this is very critical. A lot of pharma company measure the moisture effect, like going from 1% relative humidity to 99% relative humidity. All right. Why do they do that? Because they want to ensure that the tablet is stable in Sahara Desert with less than 5% humidity, and is stable in Mumbai with 80% humidity. So that study is very important, and they do this with similar kind of spectras. Okay. Here's another cool non-eminent example. Sorry, I forgot about this. Yeah, this is another nice one. So both alumina, Al2O3, and calcium carbonate are typical excipients used in pharma industry. Although they never use it at this high temperatures, but just for fun, I have taken this. This study really was done for a mining industry where both of them are found together, and they want to see how to separate this two material. So if you this is what we call a heat map or a 2D XRD data. The way you read a typical, and this reading of a 2D map is true for any 2D map. Any heat map you see in future, you can read it like this. Imagine essentially the way this 2D map was created was they measured an entire 2 theta range. Like, remember we did this moving of X-rays that covers this entire 2 theta range. So they measure it at one temperature. One dot will come on the entire plot here. Then another spectra is taken, which is superimposed over here. Then another spectra is taken, which is superimposed over here. And if you keep doing that for hundreds of temperature, and then you kind of zoom out a little and look things from the top, all you see is just lines created like this. Now the way you read the spectra is, if you notice this peak, yeah, in fact, let me put it this way: all the peaks below this 700 line are for calcium carbonate, because now this peak, this peak, this peak, this are all calcium carbonate peaks, because after 700, calcium carbonate decomposes and forms calcium oxide and releases a lot of CO2. And once calcium oxide is formed, these new peaks are for calcium oxide, not so this one. This is calcium oxide. This is calcium oxide, and this is calcium oxide. That's it. Whereas the ones that are crossing the 700 mark and remaining constant from room temperature all the way up to 900 are all aluminum oxide peaks. So this one is aluminum oxide, this one is aluminum oxide, this one is aluminum oxide, and this one is aluminum oxide, and this one as well. Sorry. So, and after 900, aluminum oxide starts decomposing into, in fact, it starts reacting with calcium oxide and forms completely new material. And they have their own version of peaks. So if I had continued measuring, I could have found which one of this is this, and which peaks here represent this, and which peaks over here represent this. That can be done as well. Or we can compare it to reference spectra. That is also possible. So this is how you can do multi-material studies in single plot. So that's all about XRD. Any questions again? I'll hope you don't have, or you do have any questions. Anybody? Okay. Okay. So let's move to XRF. I already taught the toughest technique now. The other two are very easy techniques to learn. So essentially, XRF gives you elemental composition of your material. That is the main purpose of XRF, and it can handle all kinds of samples: solid, liquid, powder, filters, fusion beads, and this is typically how their samples look like. XRF works for everything. Okay, so which all elements can we measure? All these elements we can measure. Essentially, anything from carbon all the way to uranium or rhodium, radium, we can measure everything. Even lanthanide actinide series also we can measure, by the way, using XRF. At what concentrations we can measure is color coded here. This beryllium and boron I have made a little lighter orange shade is because there are instruments and companies today who claim that they can measure beryllium and boron, and in theory and to some extent practically they do measure and show that beryllium and boron can be measured using an XRF, but these are under very, very, very specific conditions, and specific things must be met for it to be able to measure beryllium and boron. On a day-to-day regular scale, beryllium boron is very difficult to measure, and you'll know why in a minute. But everything else can be measured using XRF, all elements. Working principle, very simple. You hit an atom with a very high energy X-ray. This X-ray has enough energy to knock out one of the innermost electrons of the atom, typically the k orbit. And when an electron is removed, a hole is created in that space. Of course, atom does not like a hole. So one of the electrons from the outer shell jumps back in the K shell to fill up the hole. And obviously there is an energy gap there's an excess energy between outer and inner layers. So that excess energy is released as a fluorescence. And we measure this energy of this light and identify what element it is. Because each element has a very specific distance between its K and L, K, L, M, and orbits. The energy associated with each orbit is very specific. So we can very, very confidently tell what element is present based on the energy of the fluorescence we measured. Okay. Here's how I would picture it in terms of the line diagram we used to do in 11th, 12th energy diagram, right? So here's on top is your K line, and then one of the electrons from the K line is ejected. Now one of the higher orbit electron has to jump to K. The simplest one will be when something from the L3 jumps to K. That becomes the most common and the most frequent jump, known as K alpha 1. But if it is an L2 line that jumped, it becomes K alpha 2. And if it is L1, it is K alpha 3. But that doesn't happen. That distance is too close. That energies are not relevant. Only either of these two always happen. Sometimes something from M also jumps to K. And then we call it a beta. K beta 1, K beta 2, K beta 3, and so on and so forth. Sometimes the X-ray energy is way too high and it knocks both K and L electrons. Then obviously M has to jump to L. And then we call it L alpha 1, L alpha 2, and then or L beta 1, L beta 2, and things like that. In real numbers, when I say K alpha 1, and like I said, it is the most common one. So for a K alpha 1 of iron, what happens is something from L3, which is at energy 0.708, uh, reaches K, which is 7.11. What is left is 6.4 kilo electron volt. And this is a very, very specific number to iron K alpha 1 only. No other atom, no other element will have this exact energy. Okay, fluorescence energy, I mean. Anyway, so in terms of instrumentation, like I said, there are many different types of XRF. The primary two distinctions is wavelength dispersive and energy dispersive. And then if I look at energy dispersive, they are further classified based on the source or the method used to remove the innermost electron. If you use an X-ray tube, then we call it a direct excitation. There is another way we can do it. It's called a secondary excitation. Means X-ray hits some of the very specific material. These are known as polarizable materials, and then X-ray gets polarized because of it, and that polarized light then hits the sample, which causes the excitation. So when I say multiple electrons can be removed at a time, then it becomes confusing to find which element it is. So to control that, we sometimes use polarized light, and that will ensure only one electron is removed all the time. So that's still direct excitation in a way. Then sometimes isotopes are used. So these are radioactive material. They have enough energy in them to knock off electrons as well. So that is one way to do it. And then there are the high-end ones where you can use an electron gun, just like how we use in a SEM, scanning electron microscope uses an electron gun, for example. Synchrotron is also another way of creating very, very high energy pulses that can easily remove a lot of electrons. So based on how you excite or how you remove the innermost electron, we distinguish different techniques, and each one has a different type of instrument associated with it. In wavelength dispersive, the difference is based on how you measure. If you measure one element at a time in WDXRF, then it is called a sequential. And if you measure multiple elements at a time, you measure what you call as a simultaneous measurement. I'll explain that in a little more detail in a minute. Here's the instrumentation of. So what I'll do is I'll just primarily focus on the two main techniques, like the most common instrumentation patterns of both these machines. So for EDXRF, it's like you have a source, you have a sample, you have a detector, and then you have electronics and a software to show what is actually measured. It's pretty straightforward. An X-ray light of a very specific wavelength hits the sample, causes different elements within the sample to excite and release fluorescence. So one wavelength went in, multiple wavelengths came out, blue, pink, green came out. And the detector separates the colors out or the peaks out. And based on each color, we can say that this is aluminum, this is copper, this is nickel. So this is a bronze alloy, for example. So this is how XRF works. In ED form, energy dispersive form, we are basically dispersing the energies that came out, fluorescent energies that came out of sample. So it is energy dispersive. Now, in wavelength dispersive, we have one additional component in the chain called optics. We add some form of optics in between. What really is now happening, again, starts the same. Your X-ray hits the sample, multiple element gets excited, multiple fluorescent energies have been released. But now we use our knowledge of Bragg's law. We still use the n lambda 2d sine theta formula, but in this case, the wavelength that is coming out on my detector is different. It is not fixed. In case of XRD, the wavelength was constant. But in this case, the wavelength is different because each fluorescent element energy is different. And energy is directly inversely proportional to your wavelength. So each of the fluorescing element in the sample is producing a different wavelength light, fluorescing light. Okay. So my wavelength is different now, but I can knowingly use a very well designed crystal which has a very specific despacing that I already know. So if I have a constant spacing, I can still change this angle of the detector and crystal, the 2 theta angle, and allow only one specific wavelength to reach the detector. This way, I will only measure one wavelength at a time. This is called as wavelength dispersive X-ray. And then once blue is measured, this detector and crystal angle changes to some other angle, and then only pink will come. It moves further to a different angle, and then only green will come, and so on and so forth. So when you do this kind of measurement where you only measure one wavelength or one energy at a time, you call it wavelength dispersive XRF, and this is in a sequential manner. But I don't have time to do it sequentially, it is too long. So what I do is, instead of one detector, I place 7 detectors across the crystal. 1, 2, 3, 4, 5, 6, 7 across this entire diffraction focusing ring. And if all of them are at exactly known specific angles, that this crystal, it's specific to this crystal, then I can measure multiple elements at the same time, although they are going through a diffraction. This is called as uh, simultaneous measurement. So that what is the why should one use ED versus WD? In principle, WD is more accurate. It can measure lower concentration. It is more efficient way of measuring. ED is a very quick and dirty technique. No optics involved, no focusing of light, no aberration, nothing doing, right? So everything is like a jumbled, and we are very much dependent on the software to separate things out for us. So this is a quick and dirty measurement technique. This is a very accurate measurement technique. Okay. Application, again, now this is very simple and obvious that you want to measure elements in your sample. So there are during drug formulation we use all kinds of catalysts and all kinds of metallic things. So the government and all the USPs and everybody has set up limits because this metallic impurities are very harmful to our body. They are toxins. So we have to have exact known concentrations of them. That is where XRF can help you detect exact concentrations of these elements. Of course, heavy elements to be measured as well. A lot of these drugs are manufactured using catalyst. Most catalysts are metallic in nature, so you need to know if there are any catalyst left in my formulation. There shouldn't be any, but if it is, you can measure it. If there is any contamination that has happened, you can find it in the raw material only before you start. A lot of excipients are mineral based. I just gave you an example of alumina and calcium carbonate, right? You need to know the exact concentration of alumina and calcium carbonate as an excipient in your drug formulation. So it can help you there as well. Final tablet, again, you need to make sure it has this right concentration of all the elements that it should be present with. A lot of time it is measured in line in QC process also, but there are better techniques out there to do that. Packaging material safety wise also, because the packaging material is aluminum copper foils and you want to know the quality of those foils, so you can do that as well. So these are very straightforward examples. There is nothing rocket science in this. So then I move to the last technique, which is the easiest to understand but most curious in terms of application. So it's basically a two-step process. You have a sample, you have a source, and you have a detector. You throw light at the sample and you take a photo. Then you change the angle of the sample, like move it 1 degree. Take the photo again, move another degree, take photo again, and do it all the way around 360 degrees. So you will have 360 photos, right? And if you digitally reconstruct all those 360 photo to look at as one 3D model, then what you create is a micro CT model, 3D model. Oh, by the way, CT refers to computational tomography. So this is the final output of a typical micro CT example. So you can clearly see what I mean. It has basically taken the image of that shoe in 360-degree images, 360 images all combined together. Then it looks like this, and you can clearly now see through and through the shoe. You don't have to open. You don't have to do anything to the sample. It's a completely the main advantage, the biggest advantage of a micro CT computational tomography instrument is it's a non-destructive technique. It does not damage your sample whatsoever, and you can know what is happening inside the sample. Yeah, same idea, just a little better example. So you have your tube, this is your stage, which is rotating in nature. This is my sample is, for example, is a car model, right? So I take it in this angle, at this angle, from the back, from the side, from a southwest back angle, from the front side angle, from the other side angle, from like on the passenger side angle, and then completely flat angle with different things happening, right? And then when the model is created, it will have a complete 3D volume like the shoe I showed before. The advantage of this machine is you can slice. So why I kept this slide is because you can, these are the slices. From this 3D model, I can stop it here, and then I can take a slice of this shoe and see inside. So this is what you can see, because in this particular shoe, there is nothing to see inside. It didn't make any sense. But in a car, there are things to see inside, right? And these are different slices of that 3D model. In this case, you can see the passenger seats very clearly. In this case, you can see the wheels very clearly and things like that, right? So this is the advantage of a CT machine. That's it. This is all it is. So principle wise, it's very simple. But how would you use this in pharma, right? It's not very obvious. So here are some examples. A lot of time tablets and capsules are filled, and we have to ensure that the capsule is only filled 60% of the way or 80% of the way. You can't open and make sure it's filled, right? So that's when this CT helps you see that very clearly. Sometimes when we pack the formulation into a tablet, there can be cracks and voids formed. You don't like a tablet with a crack in it, right? So you want to make sure that cracks and voids are not formed. The porosity is the way it should be, things like that. uh, when we do dissolution studies, so this is before the tablet is formed, they do all these dissolution studies. Dissolution studies affects the final structure of your API, right? So poor formulation, is the drug being released in the controlled way that they want to release? All that can be seen using CT also. Pre and post dissolution studies, right? What it was before and what it is after dissolution and things like that. Coating, a lot of times the tablets are coated, and the coatings are released very slowly in your body, right? So the coating thickness, coating quality, there is no deformation in coating, and the coating is uniform or not, all that can be seen using CT. I already mentioned about capsule filling. How much is content, how much is filled, is it packed thoroughly, or there is a lot of pores? So when you pack something, there will be gaps in between the two powder. You want to compactly pack it or you want to loose pack it, all that can be checked using CT. Lyophilization. So when you freeze dry something, we nowadays freeze drying is very common. We have foods that is freeze dried all the time. We just add hot water and you get your ready to eat food, right? So that's essentially is the principle used by pharma also in many cases to remove the water content out of the formulation. So after the water is removed, it really damages the structure of your physical form. I mean, when I say structure, I mean physical form of the API or excipient or whatever formulation it is. So again, CT can help you see the difference of what happened before and after freeze drying. Foreign particle, of course. While it is in a factory, it is very much possible that some random foreign particle has fallen in your process and it is entered your tablet or your capsule or syringe or whatever. So if any metallic foreign impurity has entered your production process, we can easily identify that. Yeah, so you're basically going from a powder to a tablet, right? You press it, you compress it. So there are a lot of compression physics involved in this, and the cracks and voids and whatnot. Every tablet should look exactly the same. And to that extent, the CT is used to verify that all the time. And it can remove the non-uniform tablet out of the process before packing. So these are some places where CT is used very effectively. And that's about the three techniques I wanted to talk about. And now I'll take 2 minutes to give you a brief about where I work, what I do, right? So I am part of IIT Bombay. We now have what we call a central sophisticated instrument facility. This facility was created last year. Traditionally, we used to have a central facility called SAIF, Sophisticated Analytical Instrument Facility. That only used to house 18 machines, 18. Today, we have 180 instruments of CSIF. And all the major categories you can think of is covered in this institute now. we have microscopy imaging instruments. So the machines that I just talked about, we have all of them. We have XRT, we have XRF, we have CT, we have SAX, we have everything. You name it, we have all those machines. Yeah, so we have microscopy imaging, SEM, TEM, FIB, SEMs, Raman imaging, confocal Raman, all that is available. XRT, XRF, SAX, particle sizer, laser diffraction, all that is available. 3D printing, prototyping, and all that is also available. HPLC, UHPLC, HPLC MS, GCMS, 2D GCMS, GCGCMS, GPC, name it, all of them are there. Material characterization, more for automotive and hardware UTMs and 3-axis bending, testing, stress, texture, all those measurements. Spectroscopy, yes, of course, UV vis, FTIR, Raman, whatnot. Peptide synthesis, nucleotide peptide synthesis, and then synthesizers, then sequencing, genome sequencing, all that is available. Yes, we have machines for you. Yeah, these are some I listed. Maybe you can refer when you see it. So we have opened this entire facility to industry and students, academia, everywhere. You are welcome to use our facility as a testing service. You can send your sample and we can do the testing for you at a nominal charge. Other than that, we training services ourselves. We do a lot of webinar, hands-on training. This coming April, on April 6th to 10th, we are going to do a 10-day workshop on GCMS, right from basics to all the way to trace elemental analysis using different techniques. We are going to teach on GCMS, MS. So yeah, if you guys are interested, you're welcome to register. I will share the pamphlet with Sujit ji. He can put it probably on your group. We also do a lot of online webinars like this. We do a lot of modeling and prototyping. Not very useful for you guys, but for industry it is very useful. So this QR code will take you to our website where it's all the instruments are listed. You're welcome to check out and join, request us any service you may need. And I humbly thank you for your time.
Thank you so much, Dr. Sambhav. Any questions?
Is the chat? Okay. Either I did a very good job or a very bad job. I wonder what.
No, ask. You can ask questions. It's not that every day you get Dr. Sambhav to answer you. Apart from XRT, also you can ask any of the instruments. If you have
anything. Yeah, any analytical question you may have, probably. Yeah, I can handle that.
I will ask myself.
Go for it.
Yes. Okay. So from an industry point of view, what what are the what do you say a problematic or a issue that usually comes up when you are using XRD and how to rectify it? Means the commonly faced issues with respect to.
Yeah. So that's a great. Just one second. XRD, I might have made it look very simple in terms of how you measure it, but
absolutely, it's one of the toughest to handle.
Yes. So going from here to here, it's actually the arrow should be the other way around. What you get in an XRD after measurement of a sample is this. Going from here to here is the real challenge. And because unless you know a little bit about your sample, completely unknown, like just any random black powder you give me and you tell me what this is, I'll basically say, no, I'm not going to touch this sample. I cannot do this. I don't know. Because there are so many permutation, combination, and possibilities available. So the database I was talking about in a couple of slides later, we have to, of course, refer the database, right? I'll have to do search match and identify where it is this one, where it is matching, which peak is matching to a typical pattern. There are 4.5 million samples currently in the smallest database we have. How are you going to find any random sample matching to one of those 4.5 million? You can't. You simply can't. So XRD on its own cannot stand. That's why it needs support of other techniques. So one of the most common support we get is from XRF. Once I know the elements present in that black powder, so once I know it has only carbon, aluminum, and sulfur, then I can input that in my database as an information saying that find all the spectra similar to the one I just gave you with element carbon, sulfur, and aluminum present in it. Then your life becomes very easy. Then if I can give more information, it also should have a Raman peak at so and so place. Makes life even more easier. That is the real challenge, the analysis part of it. Collecting data is very easy. Any, pardon my French, any Tom, Dick, and Harry can measure XRD data. But analysis of XRD data is a whole together a new ball game.
From an instrument point of view, also, what are the challenges? Means, say for example, you have moisture-related issues or something.
Acha, so like in terms of hardware measurement issues, yeah. So one of the common problem is sample preparation. So maybe I can open this slide. It's not in here, but so no, it's the sample preparation is also very unique in XRD. Yeah, this slide may be helpful. Maybe I can explain this. So this is a truly randomly oriented packing of sample. Basically, you pack your sample holder, and you should have different orientations and different crystals on the surface. But if you don't pack it well, it is very much possible that all these big size crystals are on the bottom and all the small ones came on the top. And X-ray does not penetrate through and through. X-ray can only penetrate. It's a surface technique, by the way. Believe it or not, XRD is a surface technique. So it only penetrates only few hundred microns. So if you haven't packed well, you will not represent your sample well to XRD. And you will only see some only surface material which is available on top, which is lighter, and the heavier settle down, and you miss that completely in your measurement. And you would think you don't have it, but you actually have it. So imagine that happening to a drug. You have a formulation, and then you didn't pack it well, and you only measured the surface, and you only saw API, and one of the excipient was completely missed from measurement, and then it became a drug, and somebody ate it, and somebody died. That is what is at stake in pharma.
Okay. One question in the group: how does particle size affect XRD in pharmaceutical analysis?
Very much. Very like I just explained, right? And I pretty much answered your question. Particle size will affect how you pack your sample. You want as uniform of a particle size as possible so that your packing is as uniform as possible. One. And two, the particle size also defines how much the X-rays are going to penetrate. If you have too huge of particles, only few parts of the particle will be available for analysis. The rest of the particle will not be available to X-rays because X-rays won't penetrate enough. So very typically between 15 to 50, 15 to 50 micron is considered ideal particle size for XRD.
Okay. Another, your question with respect to online classes, I guess
online classes are available. You can go to what we call education outreach. IIT Bombay has a program called education outreach, and you can search, just Google education outreach IIT Bombay, and there are lots of courses available for you to choose from. That's one. And IIT Bombay also has a YouTube channel, I believe, where a lot of professor lectures are recorded and posted as well.
If you have any specific course, you can also share. I will share in the group. So if we
Sure.
like your GCMS program,
I'll give you the GC pamphlet. Maybe
yes,
I can.
I'll post in the group itself.
Sure.
One more question: any limitation of XRD? I guess that was mentioned in the slides.
Yeah. So XRD is this basically XRD is a dependent technique. It cannot be the only technique that helps you identify your structure or things like that. Where is that USP wala statement? That's a very important line.
Means you require supporting data.
Yeah. Single crystal. It cannot work without. That's what I was looking for. Slide. Yeah. So this is basically the biggest limitation, that XRD is a support technique and not a direct technique. एक वो प्रॉब्लम है XRD का. Second problem of XRD is it's a surface technique. It cannot measure bulk. You have to have a homogeneous sample on the surface has to be representative of the bulk. Not always possible to do. So you have to slice. Although we say XRD is a non-destructive technique, it doesn't have anything happen to your sample. But if your sample is not homogeneous, so you have layers of things. You have a few nanometer thickness layer of something, and then something else is in below it, and they are not homogeneous. They are not mixing. They are not becoming one, no matter what you do. They are, or sometimes it is knowingly done. You have coated something. Multiple layers of coatings are available. You don't want to mix them. You want to let them be separate. But X-rays will not penetrate all the way down. So you will only measure the top layer, or maybe top 2 layers, and nothing else. So in that case, you will be forced to cut the top 2 layers and then measure again to measure the bottom one. So it becomes a destructive technique in a way.
Absolutely. Means it should be done on the second stage, correct?
Yeah.
Initially, you should be doing some other technique.
Yeah.
And then
So
for
confirmation, if I have a multi-layer sample, like I just explained, like you have 3-4 layer of coating and then a substrate, I should start with CT. CT will tell me how many layers are present, because each material will have a different absorption capacity or transmission capacity, and will come up as a different shade, which you would have noticed in the image as well. Actually, I didn't highlight all that, but it is very obvious also. So here in the shoe itself, in the shoe, if you see, the lace is slightly darker color, the sole, rubber sole, is a different color, and the top fabric is a different shade. I say color, but it's a shade, right? Really, the different gray shades are available on the shoe, right? And it is different because the rubber sole is rubber. The top part of the shoe is the fabric. Fabric is very different from rubber. It interacts very differently with X-rays, and the lace is also very different material. So all different materials will have a very different shade when you do a CT. So when you have those layered sample that we are talking about, would show up as very clean layers in a CT. Even in a car example, it is very obvious. The rear, I forgot what it's called. This is a very different material than the rest of the car, because it is a much whiter. The whiter it is, the harder the material it is. The more strong the material is, and the grayer the material is, the softer the material is. So you can all that identify using the shades only. So first start with CT, then do an XRF. Again, it's a surface technique, but it can confirm a lot of at least initial sulfur information. Then you do XRD. Then you'll be able to know what the material is.
So any more questions? So anyways, we had a few questions. We are lucky to have a few questions. Okay. So thank you so much, Dr. Sambhav, and for accepting this invitation. And I sincerely hope that you will come up with, whenever I call you, you will come up with another technique, because I know the knowledge that you have in store for us. So thank you, audience, also for your patient listening, and of course, thank you for all the questions. Any comments from your side, Dr. Sambhav?
No, I'm glad you do that, and thankful you are doing this. It's very important, and I'm thankful for inviting me, and I'll be open to another talk as well in future.
Thank you so much. Okay, so we'll be posting this on YouTube also, just in case you want this as a reference. Thank you so much. Bye.
Thank you. Bye bye.
Great weekend.
You too.